So we've been part of Blue Waters from the very beginning, even before the architecture changed. So we've seen Blue Waters grow up and suffer its growing pains, but it's really been a stellar machine the past 6 years. I mean, I'm not. I think it's been great all along, and it's been a marvelous opportunity to use the machine and use the incredible resources and the help staff that comes with it. So I really appreciate this opportunity to talk about our results. This involves a large group of people. These are general relativistic MHD simulations of accreting binary black holes. So these are not what maybe you're familiar with LIGO. These are more, so LIGO detects these stellar mass black holes, then spirals from them. Here, these are supermassive black holes. So instead of stellar mass, or 10 to 100 times the mass of the sun, we're dealing with 1 million to 1 billion times the mass of the sun black holes that are in spiraling. And so these are detectable by gravitational wave detectors that operate at millihertz down to nanohertz. Primarily we're looking at LISA targets. So LISA is the Laser Interferometer Space Antenna, and that is a NASA ESA mission, or rather actually ESA and NASA. It's an ESA-led mission. And then there are pulsar timing arrays, which are networks of neutron stars that operate as clocks throughout the cosmos. And we can use their timing fluctuations to detect gravitational waves. Anyway, I'm talking while this movie is running so that you can see how this is actually a ray tracing using general relativistic ray tracing of X-rays going through really like low density materials. So this is at a low accretion rate parameterization. And you can see the X-rays coming from the gas around each individual black hole, and also the circumbinary gas around the binary. And then the accretion streams, you can also see that connect the two. And so here, we're just rotating it to show you how it changed. The image changes by perspective. And you can see as one black hole comes into the foreground of another, there's this little cool eyebrow that arises, and that's the lensed image of the other black hole from behind. So this really kind of really fun stuff to image and play around with, and so that's what we've been doing on Blue Waters. We're doing the MHD simulations and then ray tracing it to get an electromagnetic output that we can use to search for these things. So one of the broader impacts of research is that this is kind of inspiring not a new field, it's a growing field of astronomy, multi-messenger astronomy. And as I said, we're looking for longer wavelength gravitational waves and also electromagnetic counterparts to them. So here, this is just a graphic of a pulsar timing array science. So these are billion times the mass of the sun binaries that, so these are products of galaxy mergers. So you start with galaxies, they get close to each other, and they in-spiral due to dynamical friction, and they get closer together, and eventually they get into the gravitational radiation regime in which the radiation emitted by gravitational waves allows efficient in-spiraling of the binary. And so so in the top row here, you're shown, my pointer disappeared, so you can use different instruments to probe different wavelengths to explore different aspects of the gas. And you can explore at different regimes or at different separations. So from left to right, you're getting closer. You're getting closer binaries, and the frequency of the gravitational waves increases. So as you get closer, you can probe like the eccentricity distribution of these binaries through the gravitational wave signal. You get the masses of the binaries very accurately, so that allows you to pin down theories of the electromagnetic emission. So that's no longer now an uncertain quantity that arises from your spectrum, but it's something that you kind of know very well. And so then you can use these as laboratories for plasma dynamics in the strong field regime of gravity. So it's important that, so these systems are prime LISA targets, and gravitational waves allow you to localize them in the sky very well. However, in a LISA localization oval, you're going to see a large volume of space because you can see deep into the redshift distance. So you're going to be considering millions of galaxies that could be hosting these binaries. So you need accurate, detailed models or simulations of the electromagnetic emission so that you can identify these fluctuating sources as the sources of gravitational waves. So you're wanting to look in the time domain and also spectrally too to identify these sources. You're not going to be able to spatially resolve them with light. And this is also, so as I said, it's inspiring work in multi-messenger astronomy. It's also inspiring people to change their strategies for future observational campaigns. So primarily in ESA, they've got these two missions, Athena and LISA. Athena is an X-ray telescope. LISA is the gravitational wave space antennae thing that's going to fly in around 2030, 2034. And so they're going to, Athena's schedule is getting later and later, and so there's an opportunity for them to overlap. And if they overlap, then we can search for them in both gravitational waves and X-rays. And there's a great movie here on YouTube that kind of discusses the astrophysics you can do with both of them in space at the same time. So one cool thing you can do with these sources is that you can identify them before they merge and study them before they merge, so you kind of know what's going to happen, what is there as they inspiral and merge. So you can go from pre-merger, merger to post-merger and study the whole evolution of the system. Whereas LIGO, you're going to only have the opportunity to follow up on these sources. So you're never going to have the opportunity to see them before they go off. So last year we reported on results of 3 orbits. So these calculations take about 1 million blue waters SUs or node hours to perform. So they take a long time. We don't have GPU acceleration. I'm sure that would help us. But it's a little bit more complicated because we have time-dependent gravity. So we have to calculate the metric every time. We have to calculate Christoffel symbols, coordinate transformations. We use warped grids. And so all of this are matrix operations that are kind of costly. So it's a little bit more overhead than a typical accretion disk simulation would require. But and last year also I reported on our ability to calculate spectra from these sources. So we have the machinery to do self-consistent radiation predictions from our simulations using the cooling function as a proxy for the emissivity of our radiation model. And so we can get spectra going from radio to X-rays using our model. So we used that light that we calculated on blue waters, and we made educational movies that we shared with the public. And we used NASA's communication team to do this, and NASA's YouTube channel, and NASA's Twitter account, NASA's Facebook account. And we garnered about 800,000 views on these movies. And so it attracted a lot of attention. It helps to make your movies pretty too, and involve black holes, I think. So, but also NASA is a very popular website. So, but this movie actually attracted more views than a typical NASA movie. So we were really fortunate to be able to leverage those resources and share our results with the public. And we wouldn't really have thought of doing this if we didn't have the resources of Blue Waters, because it does take some effort to make these movies. I mean, each frame is about 10 million pixels, and so we have to make thousands of these frames, and because we want to make it at 4K resolution, and so that takes about 100,000 Blue Waters SUs. So this is just the beginning of the movie we made with NASA. And so I made the frames that you see here, and the communications team, the Viz people, added the text, a soundtrack. I don't know if, anyway. So, and then also they stopped and highlighted aspects of the simulation. So that was I think, a really cool addition to the movie. So I won't play the whole thing. You can go look at it later if you want. So this year we extended the simulation to 12 orbits. We were like, hey, let's just keep on going. And so the goal here is to actually get some sort of steady state in the accretion flow. So 3 orbits, it was questionable whether or not the disk and the gas was settled into some sort of steady state. And now we're kind of confident that there was a steady state between the Minidisks and the circumbinary flow. You do notice that there's a big black circle in the middle of our grid. So this grid we use is warped to resolve the MHD around each black hole. So this is the grid that we used. However, it's topologically spherical. And in order to not use a ridiculous time step size for the Courant condition, we truncated the radial grid at some finite radius at about 2m, m being the length scale of a black hole, the mass scale of a black hole. So, however, it allowed us to study the quasi-periodic fluctuations of mass in the minidisks as the minidisks travel near the lump or overdensity feature in the circumbinary disk. So there's this large mass reservoir that orbits at the local orbital rate of the disk about the binary and then feeds the minidisks. And the minidisks, as they orbit away from the lump, they deplete, they accrete the material, the black holes accrete the material around them, and then they replenish as they go past. And so this mini-disk fluctuation occurs over time, and we see that it settles down to a steady state. And we can take the Fourier transform of this, and we see that indeed what happens is there's a great deal of fluctuation at the beat frequency between the binary frequency and the orbital frequency of the lump. And so this is a non-trivial consequence of the MHD dynamics. You would think that maybe a periodic signal would be tied to would be just equal to the binary orbit, but it's actually some factor of the binary orbit. So you need to do these simulations to understand the orbital timescale so that you can connect to the orbital aspects of the binary. And so here we're just looking at the mass. We're hoping that the light will also lead to a similar periodic signal. So last year, we also talked about our results with Patchwork and the developments of the Patchwork code, which allows us to use misaligned coordinate patches. And we used them this year to perform the same sorts of binary accretion simulations. And here are some of the parameters. So Patchwork now covers the interior, the inner part, including the binary, with a Cartesian patch. Okay, so now we don't have to truncate the grid, so that inner cutout is gone. So we're covering the whole problem domain. Okay, so that's great. And it also allows us to resolve better the disk thickness. So and also it allows us to not necessarily, allows us to uniformly treat or grid the region around the black holes. So the warped grid was a little distorted in some parts. So here now it's more uniform. And here's a movie of that, and I beg you to find where that interface lies between the inner Cartesian patch and the outer spherical patch. And this is really tricky because we don't produce monopoles, right? So the div-B condition is upheld. And so if it wasn't, you would get the spurious fluctuations on the grid interface. And so it took some effort by Mark Avara, who's sitting in the front row there, to get working. So it also allowed us to run for 31 orbits or until pretty much the black hole's in spiral completely. And that's another, so this is the longest 3D MHD simulation of binary black holes. And this is a visualization showing the vertical structure of these accretion streams and the mini-disks. So there's a lot of interesting dynamics that happens out of the plane too. So there's maybe some evidence that the mini-disks are tilted, and there's also some high altitude accretion phenomenon that arises. So, and the key thing here too is that since there's no cutout, we can see how the mini-disks slosh back and forth between them. And we suspect that there's going to be a great deal of interaction between the mini-disks, and that there may be shocks that arise that dissipate kinetic energy and produce a bright electromagnetic signal. So we plotted the mini-disk masses as a function of time. That's the left plot. And we're seeing that the transition at which the truncation radius of the mini-disks is approaching the ISCO, and that leads to a decrease in the masses of the mini-disks. And then as the binaries as the black holes run away and approach merger and decouple from the gas, you see then also a drop in the mass of the mini-disks. Again, if you take a Fourier transform, you see that a lot of power is in this beat frequency, so it's still non-trivially connected to the orbital frequency of the binary. And if you compare to our warped grid results, they're fairly similar, okay? But the new results show maybe more power at higher frequency. So we're still exploring this in detail to see if these are statistically significant peaks at 2 times the orbital frequency of the binary, and but also there's a little bit of a difference at the lower frequency end. There are 2 peaks there instead of 1 broader peak, and we're wondering if this is also evidence of the interaction between the mini-disks in the sloshing region. I just want to say that we also participated in the Event Horizon Telescope Code Comparison Project. So. And the first image of a black hole was made, and the modeling team that went into that, wanted to see what the systematic error of these simulated images is. So one step of that process is to perform MHD simulations, and we wanted to see if different codes produce the same results. And so there was a variety of codes used. Hammer was used. They did super high resolution simulations of this, and these were just single black hole simulations. So I just want to cite that work. And in summary, Blue Waters has been great for us, and we've discovered really interesting periodic phenomenon of accreting binary black holes. We've been able to, we started this project with Blue Waters, and now it's in a mature state where we can actually get electromagnetic output from them and start looking for them in space. And it wouldn't have been possible without Blue Waters. So thank you.